Here's the 7.5 notes. Now, two things in here. We're looking at the linear search and the binary search. Linear search is something we've been doing all year, so we just didn't really call it that, or a sequential search. It's just the concept of going across, traversing an array or a list or a string and looking for something. In a linear search or a sequential search, you're going to start on one side and go to the other side. So maybe start on the left edge, go to the right edge. So in this problem, we're asked to find the value within the array list called values. It's just integers, so we don't need any fancy methods other than really the get method. We are working here by index, so I'll start at the left index, but I could also start at the right index, value size -1. I'm not going to use an enhanced loop because I'm interested in finding the index of the value anyway. So with an enhanced loop, I'd have to write my own sort of index tracker, which just seems unnecessary. All right, like I said, we'll go across the list. Real simple question. We go into the array list, we get a value. If it's the one that we wanted, then we return the index where it was located. If we make it through the entire array list and we never find what we look for, we're usually going to return some sort of like fictitious value. So it could be like a value larger than the size, or it could be -1 or any other negative number because you can't have a negative index. So it's just really an indicator to say we didn't find what you wanted. I'm just producing kind of 10 random ints here, and then we're searching for one. So I was looking for a 1, 4, and a 6. They found a 1 at index 1. There happened to be a 4 at index 2, and there happened to be a 6 at index 0. There weren't any zeros in the array list, so we returned -1. There were quite a few 1s. Remember, you can only return one value. The reason I returned 1 is that was the first one found. Okay, if you wanted to find the last one found, you could reverse the direction of the loop, or you could hold off on the return, maybe like track the index all the way to the end and then return it at the end. So, there's other ways that you could write this linear search, right? So for example, right here, I could say maybe like int index equals -1. So I'll kind of start with the fictitious index. If I find it, I'll set it up, but I won't return it until the end. In this case, it's still going to work. You are going to get the last index, though, if it's like a multiple occurrence issue. Just depends what you wanted. In this case, notice that there was multiple 1s. There was one at index 4 and one at index 9. My method returned 9. Okay, I also found 5 versus 3 for the 4, and for 6, I could have gotten 2, 7, or 8. My method returned 8. And it still acknowledged that there was no 0 because it was just stuck with that initial value. It never updated in the middle. Binary searches are different. So binary search, earlier this year, we wrote a program called Number Guesser where I was randomly generating a number from 1 to 1,000, and we were going to try to guess what the number was. If I played this game employing a linear search, okay, that means I'm going to start at one end and move it. Oh, I got my number lock turned off. Let me try that again. I'm going to start at one end and I'm going to just walk across the array list, or the array in this case. And I'm just going to keep looking for the number. So, all right, let me try that again with my number lock on. All right. Is it a 1? No. Is it a 2? No. I might get lucky. Maybe it is a really small number. Okay. But I don't think you really want to watch me do this. What if the number is like 900? It's going to take a while. Okay. If we did this in more of a binary search, which is considered a divide and conquer method, then we're going to play this game a lot differently. Okay. What we're going to do is we're going to keep trying to like whittle down our search range. So we start off, there's 1,000 potential values. Okay. But if I'm going to divide, maybe I'll put in 500. Well, that was too high. That lets me rule out all numbers from 501 to 1,000. So I didn't just rule out one number, I actually ruled out over 500 numbers. Okay, that was too low. Now I just ruled out everything from 1 to 250. So 75% roughly of the values are gone. All right, that was too high. So I'm between 250 and 375. And, we don't really have to watch me play this to completion, but All right, that was too low, so we're between. So 63, 31, let's go like 3, still too low. 32, 16, too high, still too high. So now we're too low. Okay, well, I think I should get it now, right? And it took me 10 guesses. Now, the significance of that number 10 is actually kind of meaningful. So 2 to the 10th power is 1028, which is greater than 1000. That was our original potential number of answers. And so it should never actually take more than 10 tries. You cut 1,000 in half, you got 500. Cut it in half again, 250. It's only going to take you 10 divisions to get it all the way down to 1. Okay. So we're going to try to now put that logic into action. And I'm going to do that using the binary search method that I have here. Okay. This is a little different though. Okay, a couple things. One is I've got the same list of numbers that I had earlier, okay, but they're rearranged. A binary search only works on a piece of data that has been sorted. Could be least to greatest or greatest to least or whatever your ordering is, but it has to be sorted in one of those two, okay? And so it is the same numbers. You'll notice like there's 2 1s, there's 3 6s, but they've been ordered. I did that using the collections.sort method. We're going to learn a little bit more about that on Thursday. Okay, so the data has been ordered. And now keep in mind that we're looking for the index. So in this case, the lowest possible index is 0. And that would always be true, right? Your lowest index would always be 0 for any array list to start. And your highest index in this case is 9. But if I wrote that a little bit more generically, I would say value size minus 1. Okay, so that's always going to be the highest index of any array list. I then have what I'm going to use is my mid index. And this is where we start seeing the divide and conquer show up. So to get my mid index, I'm going to take these 2 indexes. I'm going to take their average. Okay, so give me their average. And I actually left, I know normally average would do 2.0, but since I'm going to use this as an index, I need to keep it as an integer. So I don't actually want a double here. I'm going to fill in the control expression of this loop in just a minute, and you'll see a little bit why, okay? All right, so here's what I'm going to do. I'm going to take this mid index, and I'm going to use it to access this array list. So I'm going to access the array list, which is called values, at that mid index. Now, it's going to give me a number. In this particular case, I would have gone to index 4 and gotten the number 3. If I was searching for the number 3, that would be awesome. I could just shut this down. So like if that was the value that I wanted, then yeah, let's just go ahead and get out of here, right? Like why do anything else? We found it. But what if it wasn't the number I was searching for? What if the number I was searching for was 1 or 7, okay, or whatever? Well, now think of the guessing game. If you could tell me the number I was searching for was smaller than the number that I just found, the one in the middle, my next search should be restricted to only the values below that middle index. But if you told me the number I was searching for was larger than the number that I just found, okay, then I should restrict my next search to be only the values found at indexes above the middle index. And so that's what this loop's going to do. We're going to try to constrict the next search, and then we'll keep running the search, okay? So how are we going to do that? Well, I'm going to write an else if. It's going to look just like this one. So, I mean, I could go ahead and just copy that, okay? But instead of asking if it equals, let's ask if it's less than. Remember what we said. If the value you're searching for is smaller than the one in the middle, your next search should be restricted to only the indexes below that middle index. Notice the low index doesn't actually change. Even though we're going to the lower half, the low index doesn't have to change. It's the high index that has to change. We don't want to go all the way up to index 9 now. We want to cut the high index off at 3, okay? Or a little bit more generically, what we could do is say, go to what used to be the middle, and let's go 1 left of that. Let's restrict our search to be 1 below what used to be the middle. So we're going to be in the bottom half, in other words. Now, there's only one other possibility. The number you were searching for was actually larger than the middle. So your next search should go above the middle index, which means leave the high index alone. You still want to go all the way right. It's now the low index that you actually want to update. And you want it to be whatever used to be the middle, but let's go one to the right of it. Now, that means on your next search, you're going to have a new middle. So I'm actually going to move this line of code into the loop, okay? And I don't ever really need my mid index outside of the loop, so that's fine, okay? It can be local to the loop, no problem. I'm actually going to leave these two here, though. If I moved those into the loop, that would cause them to reinitialize with each iteration, and I don't want that. I don't want to always go from 0 to the highest index, right? My future searches are being restricted based on this code, so I actually don't want to revisit these statements. I do want to revisit this statement each time because every time I find a new searching region, it has a new middle. Now, when do I stop this loop? Okay, well, this is a little tricky. Stop the loop once the low index exceeds the high index, okay? But remember, while loops run while they're true. So I'm actually going to write that as less than or equal to. As long as I'm producing valid searchable regions, keep looking. At some point, if you don't find what you're looking for, those indexes are actually going to crisscross, and you're going to create a searching region that can't be searched, okay? Like it doesn't exist. That's when the loop needs to quit, and that's your acknowledgement that it didn't work. I recommend writing down a list just like mine on a piece of paper and running a search for a number that isn't in there, like in this case, search for 5, and watch what happens to those indexes as you search for the 5. This will make a lot more sense to you, but you have to do it yourself. Okay, it's just write down these numbers on paper and go through it. Let's see if this is producing the correct values. If you do the CS awesome, you're going to have to do this with strings and arrays, okay? And that's how we take this a little bit further, right? This code I did today was just integers list. See if you could do this for arrays as opposed to array list. See if you could do this for a string as opposed to an int. Using a string is a little tricky. You'll have to use the compare to method as opposed to just like a strict less than or greater than. I can't ask if apple is less than dog, but I can ask if apple.compare to dog is less than 0, okay? Yeah, it looks like it's working. It found a 4 at index 0. It found a 6 at index 7. One interesting thing to note is there's multiple 6s there. I don't want you to think it always comes back with the first index. There's no rule to it at all. Depending on how the numbers play out, it could be the first or the one in the middle or the one at the end. You just don't really know, okay? The last thing, and you just have to trace through it and find it. The last thing I'm going to do is I'm going to add some counters here because I'd like to show you exactly kind of how many iterations that we're talking about. Now, I'm going to put right here, I'm going to put a count plus plus. Okay, I'm going to do the same thing on my binary search. Okay, you can only return one value, so I can't return this count. Okay, but what I could do is I could put in a return. Now, I'm going to actually change this back to the way I had it before. Otherwise, it's going to take 10,000 times every time. And so I don't want to do that. I want it to have a chance to get out of here early, okay? And just so you can still see that this isn't as efficient. All right, so I'm going to add right here a system out print line that I'm just going to say something like iteration count, and I'm going to put in the counter. And I'm just going to throw a slash in there so it looks a little bit better. All right, and I'm going to need to put that print line a couple other places because potentially we're not going to return from inside the loop. We might return from here. And then real similar here, we might return from here, or we might return from here. Now, the reason I'm doing this is I want to show you how much more efficient the binary search is. If I only ran it like it is right now, like if we just had 10 numbers, then it's not really that big of a deal. But I put in a separate case here where you could try uncommenting this, okay? And this is going to have 10,000 numbers. So we're really going to see the impact of the binary search done over a larger data set. And imagine if you had a billion numbers or a billion objects that you had to check several ways to find what you were looking for. Like you had to match a name and an ID number and several other properties or whatever, or images. In your image search, you're looking for a certain number of green pixels or something. It could really, really get slow. Okay, well, all right, here's the linear search done over 10,000 numbers. When it doesn't find the number it wants, it takes 10,000 iterations to figure it out. Even here, it found the number. It took 3,590 iterations. That number could be as small as one. It could find the value on its first try or its second try, but on average, it's going to take about 5,000 runs. Here's the binary search. Okay, 13, 14, 12. That's a lot smaller on average than 10,000. That 14 is the largest number you should ever see. Okay. And the reason is if we look at 2 to the 14th power, it's greater than 10,000. It's the first power of 2 greater than 10,000. And as a result, okay, we should never need more than 14 binary searches to find any number that we're looking for. Now, there is a catch. Remember, I had to sort this data to make this work. That actually took much more than 10,000 iterations of a loop to do that. We're going to learn that later when we learn our searches or sorts next in a couple days. So I did have to spend all that time sorting it, but then I saved all this time searching it. If you were only going to search the list once, linear search, okay? Because then you don't have to sort it. But if you're going to search multiple times like we did here, then the binary search in the end is going to become much more efficient.